Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CC student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The problem that we are going to discuss today is expected number of strongly connected components. The problem appeared in January Long Challenge 2021 and has a difficulty level of medium. The prerequisites for this problem are probability and Euler's formula for planar graphs. The problem statement goes as follows. Given an M cross N matrix and an integer k, the cells of the matrix are filled with random integers between 1 and k inclusive. And after that, a graph is then built on this matrix. A directed graph is then built on this matrix in the following manner. Two cells containing the values x and y have a directed edge from x to y if these two cells are first of all adjacent, that is side adjacent, and the value x is greater than or equal to y. So a directed graph is built in this manner in this matrix after filling the values. Then what is our task? Our task in this question is to find the expected value of the number of strongly connected components in this graph. So definitely we would get a directed graph out of this matrix, some random graph, right? We have to find the expected value of number of strongly connected components in this graph. To begin with our solution, first of all, we need to understand that the given problem is that on a directed graph where the edges are between adjacent cells if x is greater than equal to y, and we have to find the expected value of number of strongly connected components is equal to finding the expected value of connected components in an undirected graph such that the edges go from one cell to another if they are adjacent and have equal values. Why this is equivalent? Let's see. So we are going to prove our point using proof by contradiction. So our assumption is that x and y are adjacent cells in the same strongly connected component such that x is greater than y. So we have assumed two adjacent cells, and by definition, so there will be an edge from x to y because they are adjacent and x is greater than y, right? But note that according to the definition of strong connectivity, there must also exist a path from y to x because they are in the same strong connected component, right? Let's see if that is actually possible. We know that with every outgoing edge, that is, let's say if there's an outgoing edge from this cell containing y, wherever the edge goes to, that cell contains a value less than or equal to y. Why? Because according to the condition given in the question, if there's an edge from u to v, then the value of u must be greater than or equal to v, right? So with every outgoing edge, the value either stays same or decreases. This means that there can never be a path from y to x. Why? Because we have assumed that the value of x is greater than y. So this contradicts with our assumption that x and y are in the same strongly connected component. So now it's pretty obvious, and most of you must have guessed by now, that for two cells, that is x and y, to be in the same strong connected component, their values must be same, right? If and only if their values are same, then they can lie in the same strongly connected component. But what this also implies is that now there's no meaning of the directed edge. Why? Because let's say that there are two adjacent cells containing same values, that is x and x, then the edge would be bidirectional, right? Because x is also greater than equal to x, and again x is greater than equal to x. So the edges would be bidirectional. So that is why we have reframed our question such that initially it was on a directed graph uh, where the edges were from x to y, where x was greater than or equal to y. But now it is on an undirected graph, as you can see, and the edges are from cells x to y if they are adjacent and have the same value. And because it is an undirected graph, uh, we have to count the expected value of connected components rather than strongly connected components, because it is one and the same in the undirected graph. So now we know that this is our new problem and this is our old problem. We have just reframed it into a new problem. Let's see how to solve this new one. So now to solve our new problem, the first main observation is that the graph that we are going to draw is planar graph. What do I mean by that? We know that a planar graphs are those in which the graph can be drawn without any two edges crossing each other. And you can see for yourself that by construction, any graph that you draw for the given question and the constraints will always be a planar graph. That is, no two edges will cross each other, right? So now that the graph is planar, there's an interesting property of planar graphs that is known by the name of Euler's formula. What the property says is that V minus E plus F is equals to 1 plus K. That is, for a general planar graph, the number of vertices minus the number of edges plus the number of faces in the graph is equals to 1 plus number of connected components in the graph. What are the terminologies again? V stands for number of vertices, E is the number of edges, F is the number of faces. For those of you who don't know what do you mean by faces in a graph, assume that if there's a plane and you're drawing the graph on the plane, right? Because it's a planar graph, so it can be embedded on a plane. So if you draw the graph, then after drawing the graph, whatever is the number of regions that the plane is divided into, that is nothing but number of faces. For example, here you can see that the plane is divided into two regions, that is this outside region and one is this one. This is another region. So that is the number of faces and k is the number of connected components in the graph. So once we know this formula, what we have to find is the expected value of number of connected components, right? So we can rearrange this formula to get this, right? So we can rearrange the terms to get this formula, and now we can see that coming back to our original problem, we have to find the expected value of k, and that is nothing but the expected value of the right hand side. And now using linearity of expectation, we can split it like E of k, that is expected value of number of components, is nothing but E of v plus E of f minus E of E minus E of 1. So our question was to find the number of expected number of connected components in the undirected graph, but now our task is to find these four values, and once we have these four values, we can simply perform addition and subtraction operations on them to get our desired expectation value. So let's see one by one how to calculate these four quantities. So the first one, that is expected value of number of vertices, is again an easy one. Why? Because it's a constant. The number of vertices in the m cross n matrix is nothing but m cross n. The number of vertices are a constant. So that is nothing but the expected value of number of vertices. Moving on, we have to find the expected value of number of edges. So we are going to use the idea of contribution over here. That is, we'll calculate the contribution of each edge in the expected value. So for two cells x and y, there will be an edge, undirected edge, right? If and only if both these values are equal. So what is the probability that this edge exists between these two adjacent cells? The probability is 1 over k, 1 upon k. Why? Think of it in this way, like there are two adjacent cells and you are fixing this value x, then what is the probability that the other value is also same as x? It's 1 by k, right? So for each edge, the probability is 1 by k, and each edge is, that means, contributing 1 by k in the expectation value. So using linearity of expectation, again we have to just count the number of edges, and number of edges into each contribution, that is 1 by k, is nothing but the expected value. So in the m cross n matrix, there are total m cross n vertices. So if you try counting the number of edges that you can draw in an m cross n matrix, it will come out to be n into m minus 1 plus m into n minus 1. So this is the total number of edges, and each of them contributes 1 by k. So this divided by k is nothing but the expected value of number of edges in the graph. Now, to calculate the expected value of number of faces, we see that there are only two cases, m is equals to 1 and m is equals to 2. Why? Because if you have read the constraints correctly and carefully, m can take only value 1 or 2. So I have drawn both the cases on the plane. So this blue box that you can see is nothing but a plane, and I have drawn the vertices initially. So to calculate the number of faces, uh, it is pretty obvious in the first case, that is m is equals to 1, that there will be only one face in any case, because even if I draw edges like these, okay, if there are edges, then in any case there is only one face in the plane, that is this outer face, right? So for m is equals to 1, the value of E of f is straight away 1. Okay, but just for m is equals to 1 case. And I'll mention over here that this is nothing but the outer face. But for m is equals to 2 case, I have drawn the vertices, and you can see that I can divide the plane in more than one region. And also the faces that we would be creating will look like a 1 cross 1 unit square. Okay, how? Let's see. So assume that I fix a value for this vertex, let's say, and the value is x. Then to be for an edge to exist between these two vertices, the probability is again 1 by k, and then the value here will also be an x, so there would be an edge. Again the value here would be an x with the probability 1 by k, so there would be an edge. And if the value here is also x with the probability 1 by k, then there is also an edge over here. But in the process, you also observe that because now both these vertices also have the same value, there will also exist an edge between these two vertices, hence creating a face, because now you can see that the whole plane is divided into two parts. Similarly, what we are saying is that we can only have faces that look like this 1 cross 1 unit square. So what is the idea how we are going to calculate the expectation value of the number of faces? Again, we would be using the idea of contribution, that is how much each face contributes to this expectation value. So first of all, we have to calculate the total number of faces. So the total number of faces is what? We can have one more like this, one more like this. So at max we have how many? We have 1, 2 and 3 faces over here, and the n was 4. So that is, in general, we have n minus 1 unit squares, that is n minus 1 faces, and each of them contributes 1 divided by k cube to the expectation value. Why? Because we saw that if we fix same idea as before, if we fix a value x over here, this has the probability 1 by k, this is again the probability 1 by k and 1 by k. So 1 by k cube is the contribution of each face, and the number of faces are n minus 1. So the total number of what is the total expectation value? The total expectation value would be n minus 1 divided by k cube, but there would be also an additional plus 1. Why plus 1? Because there's this outer face which we are forgetting. We are only right now we were only focusing on these faces, right? These faces formed by the edges, but there is always an outer face which we also saw in this m is equals to 1 case, right? So this outer face is also counted, and hence the expected value of number of faces is n minus 1 divided by k cube plus 1 in case of m is equals to 2. Otherwise, for m is equals to 1, the value is 1. So now we would be moving towards writing the C++ code for this problem. So by now most of you have understood this solution and you are free to implement yourself. But if you face any difficulty, you can come back and watch the implementation by yourself. So coming to the implementation, uh, we simply have the modular math functions as we require them for performing the modular operations. So standard functions like add, multiply, subtract, power, and modular inverse. So we start with our code by taking the input m, n, and k, and then we have our four quantities, that is expectation value of e, f, 1, and v, and also an additional variable answer. So first we calculate expectation value of v, which is nothing but multiply n with m. All are modular operations. So the function take care of all the modulo things. Then similarly, we also calculate expectation value of e, that is nothing but n into m minus 1 plus m into n minus 1 divided by k. So expectation value of E is calculated. For expectation value of F, initial value is 1, which stays same if the value of M is 1. But if the value of M is 2, as we have seen in the solution, we have to add n minus 1 divided by k cube in the quantity. So that we have done. And then finally, once we have all the four quantities, we just add EV plus EF and then subtract EE plus E1 from that, and we have our final answer. So once we have our final answer, we just output it. That pretty much sums up the implementation. So let's submit this on CodeChef ID. So while this code is running, I would like to tell you that we at CodeChef have many mini courses for competitive programmers, so that you can learn various concepts like backtracking, number theory, graph theory, and these concepts are the ones which are usually applied in the uh, problems and the contests. So we mention the prerequisites so many times, right? We mentioned the prerequisites many times, but where to learn those things from? So this is the one-stop destination. You can go to our YouTube channel, that is Learn Competitive Programming with CodeChef, or you can head to our Unacademy course as well, where all these mini courses are provided for free, and you can learn them from top world-class educators like Sanket Singh, Riya Bansal, or Pulkit Chabra. So you can head over to that and learn these concepts and then apply them in the problems. Also, this is the free material, and we have a lot of free content for you, both available on YouTube and as well as Unacademy. So the links are given over here. You can go to this page. This is available on CodeChef under practice and learn under CP tutorials. So you can head over to here and access all this content. But if you want to access even more structured content with more language preferences like Java, Python, C++, we have many courses on Unacademy as well in the paid subscription, where you can use my referral code DarshanCode25 for instant 10% discount. So coming back to our question, we see that we have got AC. So great, our solution works.